My name is Julian. I'll be presenting our work on confidentiality preserving big data analysis. This is joint work with Savvas, Russell, and my advisor, Professor Patrick Eugster. So we're all here at this HotCloud conference today. We believe that the cloud has great potential. And one big impediment against more wide-scale adoption of cloud as a not just storage but also as a compute platform is some of the reports like these. So these are a couple of confidentiality compromises which occurred just in the last week. So there's a website, privacyrights.org. I strongly encourage all of you to check it out, which lists commonly occurring data thefts. So these are two reports that happened. One where a patient record was stolen from a hospital, and second where we had a case where credit card information was stolen from P.F. Chang's. And these are reports in just the last week. So when we talk about confidentiality in the untrusted cloud, the holy grail currently is fully homomorphic encryption. So what fully homomorphic encryption allows us to do is we take our plain text data, encrypt it, place it in the cloud, and you can have an untrusted process to compute directly on the encrypted data without ever decrypting it and produce a result which is again encrypted. So even though the process is untrusted, the process is never seeing your plain text data. And but the disadvantage of doing computation like that currently is that the overhead of doing this is very, very high. And also, even the latest fully homomorphic libraries offer very limited expressiveness for the developer. What I mean by that is the developer, if he wants to compose any complex operation, he will have to compose it manually using almost register level addition and multiplications. So to talk about partially homomorphic encryptions and how it differs from fully homomorphic schemes, a partially homomorphic crypto system allows you to perform a certain kind of operation over encrypted data. For example, the Pallier scheme allows you to perform additions over encrypted text, but not multiplication. Similarly, El-Gamal or even the unpadded RSA allows you to perform multiplication, but you can't perform addition. So the conjecture for this work is that for many big data analysis jobs, we can perform them securely using a combination of these different partially homomorphic schemes and not pay the price of encoding everything in a fully homomorphic encryption scheme. So just formally, really quickly, some of the terms which I'll be using in the talk. So I already talked about partially homomorphic scheme. And within a partially homomorphic scheme, we can say that this is homomorphic with respect to addition. If I have two operands, x1 and x2, and I have the encrypted versions of them, denoted in this example by E of x1 and E of x2, I perform some operation chi over the encrypted text. If there exists some operation which we can perform over the encrypted text, take the result that we get after performing the operation, decrypt it, and the result if we get is equivalent to the result of adding x1 and x2 in plain text, we say it is homomorphic with respect to addition. Similarly for multiplication. Also, we can say an encryption scheme is deterministic if x1 always encrypts to the same value, or in other words, there's no randomness injected in the encryption process itself. Recently, not too recently, we also were able to develop, the community has been able to develop auto-preserving encryption, which means that if x1 is, whatever is the inequality between x1 and x2, that is preserved even after encryption. So if x1 is less than x2, I encrypt both x1 and x2, I still have my inequality preserved. So I won't talk about MapReduce as such, but I'll mention a couple of lines about Pig Latin on which our solution is based. So Pig Latin is a high-level data flow analysis language. It is very kind of similar to SQL queries in which you can write your data analysis scripts. And the Pig execution engine will compile this Pig Latin scripts into MapReduce programs which can be executed on a MapReduce engine, typically Hadoop. Okay, so our goal in starting this work was to perform big data analysis jobs in an untrusted cloud and do it in a way that it preserves confidentiality. And we wanted to leverage partially homomorphic encryption whenever possible. We used a couple of techniques, which we will see in a couple of slides. So what we fundamentally try to do is we transform big Latin scripts, which a developer writes or write on plain text data, and we transform it so that it can work on encrypted data as well. So as a quick example, let's look at this big Latin program right here. What it does is it loads an input file of name by name input1. It contains two columns, A0 and A1, and then it filters the input file it filters out everything that is less than 10, and once it gets the refined results, it performs a group by. So it does a group by, and then for each group it finds the sum. So we can think of this very much as a SQL query, select star from table column 1 greater than 10, and then in the next line on the results we are running group select sum of column 1 group by column 2. A very typical query. And let's look at a few sections of the line. I'll explain this slide bottom up. So if you could look at the last portion where we're deriving the relation E, in the plain text query which the user writes, we can see that the user writes something like, for each D, generate group as B0, he's selecting the group by column, and then find sum of A0 as B1. So there's an alias operator as well. So what we will do is we'll translate that into our target script. When we translate that in the target script, you can see that the sum operation gets replaced by an encrypted version of sum. So there's no magic here. What actually happens is when we talk about sum, we talk about performing addition between two operands. Now, if you want to perform the same sum over encrypted text, for example, if A1, A0 and A1, if two values x1 and x2 is encrypted under the Palier crypt system, and I want to perform addition, in Palier, what we have to do is we have to take the two encrypted texts, multiply them, and perform mod n squared, where n is part of the public key. So that is how we perform addition on encrypted text. So this ENC sum operation here performs that. And if we look one level higher, if you see the filter operation, so the user wrote filter by A0 greater than 10, and this script will be running on the encrypted version of inputs, right? So we will be using encrypted version of A0. Let's for now assume that we have an auto-preserving encrypted version of A0. Then our transformation process will encrypt 10 in an auto-preserving encryption scheme. So that is encrypted value that we see here. And further, ideally, I should be able to write A0 OPE greater than that encrypted text. But here we run into a little limitation in Java or Big Latin, which uses Java behind the scenes. So the encrypted value of 10, if we use a 256-bit or 512-bit encryption, it's too long to be represented using a Java int or Java long, which are the two data types natively supported by Big Latin. So to overcome that, what we have to do is we are representing the encrypted text as a hex string, and then we use our own function, which converts this hex string into a big integer, or in our implementation, the GMP library, which can handle arbitrary precision numbers and perform the comparison. Another interesting thing, if you observe here, is that in both the examples that I talked about, we are using the same column A0. In the very end, where I was deriving E, I'm using column A0 for sum. And the filter example I talked about, I'm using A0 to perform a greater than comparison. So we can't do that using partially homomorphic crypt systems. We cannot perform that So what we do is when we perform the load, we load A0 in two different encryption schemes. So the load statement becomes from A0, A1, and when we are loading from the encrypted file, we load both the OP version of the encryption as well as the additive homomorphic version of the same column. So this is the full script transformed. We already talked about a couple of lines. I'll only briefly mention about the third line, line 3, group C by A1 det. So in the cases that we saw so far, we had the operator explicitly defined. But here, I just want to point out that there are some operators like the group by operator where even though we don't have an expression in place, the relational operator requires certain characteristic of the operand. For example, the operand used in a group by must be deterministic, otherwise we can't form the groups properly. So just to pause briefly, we already talked about confidentiality in the cloud and what our system does. We will talk about the architecture and how it does what it does, and then I'll also show some quick results, and then I'll conclude. So our architecture itself is fairly simple. There's a pig script which the user writes in plain text. That pig script gets transformed using the process. The pig script gets transformed like I mentioned before, and the transformed pig script is submitted by the coordinator to a pig server which is running in the cloud. And then the pig server also uses the set of user-defined functions which is similar to the enc sum function which I showed. And the encryption service here that you see has the mapping between the input file and the encrypted file. So in our implementation, the encryption service is nothing but a bunch of XML files. So it says this is input 1 in plain text, corresponds to enc file name 1 in encrypted text. It'll say something like column 1 in plain text corresponds to column 3 in the encrypted file, and so on. So this is how we actually perform the transformation. We first do the script analysis, and we generate the data flow graph. This is something which Pig does automatically already. We just tap into that. And in this data flow graph, all the relations that we saw, like A, B, C, E, they're actually nodes. And the data flow between these relations are the edges. And as a next step, we kind of separate out the columns and expressions from this data flow graph, and we track the lineage between them. To show a quick example, if you look at this Pig Latin script, it's a slightly modified version of, slightly bigger version of what we saw before. On the right side, we see all the expressions extracted out. So I have the A0 greater than 10 as an expression tree on the top left. I have sum of A0 somewhere in the right middle. And also, I talked about the group by operation and the group by requiring operands to be in a deterministic form. So that is, in order to show that as an expression tree, we insert this deterministic operation, which is nothing but, which asserts that this operand is deterministic. So from here, we kind of start to get a picture of how we can deduce the final transformation. So when we scan this set of expression trees, and we can see that the node A0 is appearing twice, once under sum and once under the greater than operation. So that'll give us the first insight into understanding that A0 has to be loaded twice. We need two versions of A0. The real picture is slightly more complicated than this because all the operands may not be operands directly available in the input or encrypted file. There may be operands that are generated as part of the transformation process also. So going forward, so once we identify that these are the encryption schemes that we require at these stages in the Pig Latin script, then we use the encryption service to identify what are the encryption schemes that we have already available. Using this information, we can actually perform the transformation. So our transformation occurs at a data flow graph level. We have the source data flow graph, and we convert that into a target data flow graph. And the main changes that happen is we load from an encrypted file, we replace the columns with the encrypted version of the columns, and we replace the operands or the functions by the encrypted version, their encrypted equivalents. So to give a full picture, it is not always possible to perform all operations using partial homomorphic systems alone. So if you look at this example, I have a case where I have two columns, A0 and A1, And even though I have them available in an additive homomorphic form, I can perform A0 plus A1, but here the expression is one step deeper. So I cannot perform, so if I do A0 plus A1, the result that I get will be in an additive homomorphic encryption scheme. I cannot use that to compare with 10, even if I encrypt 10 in an order preserving form. So there's a slight mismatch here. And right now, to overcome this, what we are doing is we re-encrypt the operation that we do, re-encrypt the result that we get after the addition, and this result is re-encrypted in whichever form that we want, in this case an order preserving form, and then we perform the comparison. So in order to test some of these concepts, we have some preliminary results. So we ran benchmarks over a PigMix2 queries. PigMix2 benchmark, which is a standard Apache benchmark on which Apache tests their system pig on every release. We ran them over EC2. And for a large number of scripts, so the PigMix2 contains around 17 scripts. For a large number of scripts, we are able to perform this operation over encrypted data with around a little more than 2 times overhead. There are some operations you can see in L9 and L10 where the overhead was around 3 times higher. But what we're trying to show is there's a huge case where we don't have to depend on fully homomorphic encryption and still be able to compute directly on encrypted data. So to discuss here the limitations of what we have currently, the Pig-Latin itself is a query-based language. It doesn't support iterations by default. You have to embed Pig-Latin scripts in Python or Java to allow iterations. We don't support this right now. And UDFs also, we support the built-in UDFs, that is built-in UDFs, or if the user writes an arbitrary function, then we won't be able to process that directly. Another thing that we have to keep in mind is even though the data itself is encrypted, we are not hiding the data access pattern. So the attacker can know that there's a filter operation that's going on. The attacker can know that 2 data sets are being loaded and joined. So that information leak is still not prevented. I hope I'm doing good on time. Just to a quick related work, CryptDB has been the seminal work in this direction. CryptDB is a database system on which we can perform SQL queries without sacrificing confidentiality. CryptDB doesn't really have any parallelism built into it, so we want to exploit the parallelism offered by MapReduce as well when we perform this big data analysis jobs. I strongly recommend all of you to read the CryptDB paper. So Mr. Crypt is a recent work that appeared where they tried to translate some of the tasks at a MapReduce level. And DepSky is a storage-based solution which uses secret key sharing. So in conclusion, confidentiality is a concern, and one of the big concerns preventing more wider adoption of cloud as a platform. And it is not just fully homomorphic encryption, but also partially homomorphic encryption that has great potential in this direction. So in our proof of concept, we use Pig-Latin-based big data analysis jobs, and we were able to perform this with around 3x overhead. And in future, there's a couple of things that we are trying to do, and one of the things is that we are trying to do expression rewriting. So if I have A plus B times C, I can also write that A times C plus B times C, right? So some of these things would allow us to reduce the cost that we have to incur during re-encryption, because if I already have A and B in one encryption form, and the operator most suited for that is, let's say, addition, and the user just wrote it as A plus B times C, there are cases where I can reduce the cost of re-encryption by rewriting expressions. We're also looking at sampling-based heuristics to identify better execution paths. So you have the data flow graph. can we push operators up and down? And we are looking at some heuristics to do that. And we're also looking at to do confidentiality setting at a field level. So what I mean by that is if I have an input file with 2 columns, if the developer can specify a column 1 is not confidential, it is data already available in the public domain, then I don't have to incur the cost of encrypting column 1. It is already available to everyone. So what is the user says column 1 is public, column 2 has to be highly secure, and so on. What kind of expressivity can we get when we run queries over such data specified in such a format? And that is all I have. Thanks a lot for your patience. Any questions?
When you were comparing to CryptDB, I was a bit surprised to see you mention that parallelism was the big issue there, because it would seem for things like filters and group by, the examples you showed, that the parallelism's pretty simple in that case. So I'm wondering what you see as the bottleneck for doing parallelism with encryption.
CryptDB itself is a database engine based on MySQL, and it doesn't. So what we are trying to do is we're trying to do this on a much bigger scale in the cloud using MapReduce as well. So we are trying to leverage the parallelism offered by MapReduce in this case.
Yeah, but they chose MySQL just because it was handy. They could have easily used Shark or something like that, and it would be parallel, I believe.
Sure, but another thing that CryptDB doesn't do right now is that they don't do re-encryptions. So in cases where we have, you have, like the example that I showed before, like A plus B times C, where A and B is also generated, then CryptDB will have to rely on fully homomorphic encryption, as opposed to re-encrypting the output of A plus B, like we are doing.
Okay, I didn't understand the re-encryption part of your talk, so I will.
Okay,
talk
I can talk to you later.
Hi. So maybe you can talk a little bit about how knowing about the operators leaks information to an attacker or to an adversary. I imagine that you can glean probably a lot about the database schema from those operators, and that could be probably pretty bad.
Yes, that's true. So I guess there is a different line of work where, people who focus on, and there are people who work on trying to prevent that as well. But if we want to allow computation to happen in the cloud, so the compute engine will have to know. The compute engine will have to know that this is the computation to be performed. So we haven't. So definitely, certain amount of data can be leaked, like the access patterns can be leaked. But what that amounts to is something, an entire different work on itself, I would say. So by knowing that there's a filter operation followed by a join operation, how much information can be reconstructed using that? That'd be a big work by itself.
Do you think maybe some kind of basically operations on a transformed space could kind of cover up those weaknesses somehow?
Do you mean like obfuscate the expression itself, or?
Right. So obviously, from my talk, I'm kind of thinking about compressed sensing, and compressed sensing can be, in a way, thought of as a homomorphic kind of encryption, because you're projecting from a high-dimensional space to a lower-dimensional space, but you're kind of hiding the original information, right? And some of the operations that you do on the low-dimensional space are transforms of what you would exactly do in the higher dimensional space. So.
Sure, definitely. So any less information that we can give to the attacker about the data access patterns definitely helps. So if the access pattern is different from the original, then that definitely helps, yes.
Cool. All right, thank you.
Things like order preserving, right?
Yeah.
So just great work. You're only losing 3x. Give us a ballpark. How much a full FHE would how expensive it would be?
So we were not able to evaluate using full FHE because I guess the HElib, I don't remember the exact number, but the HElib library, which is the most common or maybe the only commonly available library available for fully homomorphic encryption. If I remember correctly, an additional multiplication operation takes in the order of milliseconds, one single additional multiplication operation. So we were not able to implement or test or have an implementation with fully homomorphic encryption because that was just not practical right now. So it should be much higher than 3 orders of magnitude, yes.
The other question I had was the re-encryption.
Mm-hmm.
So basically you have to ship all the data back to the trusted base so they can unencrypt it in the current style and then encrypt it.
Back in the,
and
yes.
ship it back.
Yes.
So it seems like it's actually the transfer of all that data back and forth.
That is, yes, that is correct. And there are a couple of things that we can do slightly better in the sense if there's like a very big expression, like A plus B times C times D or whatever, then it is not always that we have to re-encrypt the whole part. So we can think of it in this way. We can send the operands in encrypted form to the client, and the client will have to produce the result, and then the result the client can send back in whichever form it is requested. So if I do A plus B times C, client will have to compute the result, and the result will have to be sent back in whichever form.
The whole expression of the client.
Yes, yes, but yes, you're correct that that is the main overhead in that case.
Does that show up in any of the pig mix?
Yes.
Any other questions? Okay, let's thank all the speakers in the session for.
Thank you.